Hi everyone! Welcome to part 3 of chapter 25. Where we left off last time, we were talking about valence bond theory and how that was allowing us to look at the geometries of complex ions and coordination compounds. But we said it wasn't very good at predicting the color of these compounds or at predicting their magnetic properties. So I told you instead we were going to look at crystal field theory for those topics. So that's what we're doing today. We are learning about crystal field theory. So crystal field theory is going to explain the color and magnetism in terms of the effect of the ligands on the energy of the d-orbitals of the metal ions. So if you think about the d-orbitals normally, right, we have 5 d-orbitals, and they are all going to be the same in energy. So we call these degenerate. They all have the same energy. But when we have ligands on our metal ions, it changes the energies of these orbitals, and it actually causes them to split, which is what we're going to talk about for literally this entire lecture. We're talking about the splitting of these orbitals. Okay, so we're looking at how the ligands move the energies of the orbitals on the metal ion. So again, the bonding of the ligands causes the energies of the metal ion to split, these d orbitals to split, okay? The metal ion normally will have all of these d orbitals degenerate, right? The same energies, but again, when we start to interact with these ligands, then they'll split because they have different shapes. So not all of these orbitals have the same shape, right? If you remember, we have s orbitals that are spherical, and then we have p orbitals that look like dumbbells, and then we call d orbitals double dumbbells and a dumbbell with a donut. And so we'll look at those in a minute, but they all have different shapes, and therefore they are going to interact with the ligand differently, which can affect their energies. Okay, and then the splitting of these d orbitals, how much they split, depends on how they're going to interact with the ligand. Okay, so some orbitals will interact with the ligand more than the other ones, and we see that here in this picture. So we have the ligands at the top, or the orbitals at the top, are going to interact a lot with the ligands. Okay, so the way that this looks, so this is our double dumbbell with a donut. That's the middle there, but all of the other ones are going to be double dumbbells just because they have the 4 lobes. Okay, and so all of these negatives, these are going to be the ligands, because if you'll recall, right, our ligands are going to donate their electrons to the metal ion. Okay, and so we're representing the ligands with these negative, essentially, electrons. Okay, so since these ligands are on the same axis as the orbitals, same here, right? They're on these axes here. Okay, and so since the ligands are actually on the axes with the orbitals, they're going to have a really large overlap, and it's actually going to have a really strong repulsion from any unpaired electrons that could exist in these orbitals from the metal ion itself, right? Because the metal ion doesn't necessarily have no electrons. It could have no valence electrons, but it can still have some. And so if there are electrons that are in these orbitals, then they are going to be repelled by the electrons in the ligand. Okay, and then the ones down at the bottom are not experiencing these same repulsions, because if you can see, let's see if I can draw it. So here's our axes, right? And so the ligand is actually going, or sorry, the orbitals are going in between these axes, and so they're not interacting with the ligands as strongly, so we have weaker repulsions. Okay, so these orbitals will experience a higher energy than these orbitals because they are experiencing those repulsions. Okay, so that's what all of the words on the left are talking about there. Again, we remember this as, double dumbbells. We have 4 double dumbbells and a dumbbell with a donut. Okay, so again, like I said, the ones at the top, any electron pairs that are in those orbitals are going to experience really strong repulsion, and that will increase the energy of those orbitals. The other d orbitals, since they're not really interacting with the ligand as much, they're not going to experience the same repulsion, so they'll get kind of weaker repulsions. And what it does is it looks like this. So this would be our normal metal ion, right? Those are our 5 d orbitals. They are degenerate. They all have the same amount of energy. And this is, no ligand. This would just be a metal ion floating around in solution by itself, or, wherever that metal ion is. Okay, when it experiences an interaction with a ligand, then it is going to split. And I want to point out this is for octahedral complexes. Okay, so this is when we have 6 ligands bonded to our metal ion. We're going to talk about other ones later. This is going to be the most common. This is the one that I would like you to have memorized for the exam. Okay, octahedral. So we have our 3 down here at the bottom that are experiencing kind of weak repulsions. They are experiencing repulsions, but they're weak. So that's why we see these three orbitals are a little bit higher in energy than the metal ion normally, but not really, really high because they're only experiencing weak repulsions. These ones up here are much higher because, again, we have the ligands that are directly interacting with the unpaired electrons, with the paired electrons in those orbitals, okay? So they're having really they have a lot of overlap, so they're experiencing really strong repulsions, which causes them to be much higher in energy. Okay, so that's where we're getting those energies from. And then you'll see this triangle here, and this triangle is the crystal field splitting energy, and we represent it by the symbol delta. We use delta a lot in chemistry. We use it as heat. We use it here as a crystal field splitting energy. Sometimes we'll use it as change. So you should be familiar with that, but maybe not in this particular scenario. So we have our crystal field splitting energy, and the size of that energy, okay, is going to depend on a couple things. The first of these is the kinds of ligands, and that is going to be what we are mostly going to focus on, is the type of ligand that is going to be bonded to our metal ion. We have strong field ligands, and then we have weak field ligands, but so it's always going to be dependent upon the type of ligand that you have. It can also depend on their positions on the complex ion. We're actually not going to cover that in this class just for the sake of time, but it does depend on where the ligands are at. And you can imagine, right, we have a bunch of different positions. So if your ligand was here, right, it would cause fewer repulsions than if your ligand was here, okay? And then it also depends on the kind of metal ion and its oxidation state. So we're also going to look at the oxidation state of the metal ion. Is it a 2+? Is it a 3+? In general, if we have a higher oxidation state on our metal ion, we're going to have a larger crystal field splitting energy. Okay, so like I said, we're going to focus a lot on the ligands. So the size of that energy gap, right, that delta, depends on the type of ligands that are attached. So we have strong field ligands that are listed here. And then we have weak field ligands that are listed here, okay? I will give you what's called the spectrochemical series that's going to show you all of these ligands. So I don't need you going and memorizing the spectrochemical series, but I do need you to know how to use it, okay? So you need to know, I would know that cyanide's the strongest, maybe iodine's the weakest. So if you see this, you know which order it goes in. But strong field and weak field. So strong field ligands will cause a lot of splitting. Okay, there's going to be a very big delta, right? A very big crystal field splitting energy. And a weak field ligand will not split it as much. Okay, so that's going to, be a smaller value of delta. The size of the energy gap also depends on the type of cation, like I was talking about before. In general, really large charges is going to have a really large splitting energy, whereas smaller charges do not. This is because the greater charge on that metal ion is going to draw those ligands in closer. And if it draws those ligands in closer, then we're going to have greater repulsion with the d-orbitals, right? And, any paired electrons or lone pairs that are existing in there. And again, more repulsion will give us a larger crystal field splitting energy. Okay, so this is just kind of what it looks like. So if we have a weak field ligand, again, we're going to have a really small value of delta. So that's like water here. Water is a weak field ligand. And if we have a strong field ligand, then we're going to have a very large value of delta. And that would be something like cyanide here. That's very strong, a strong field ligand. And as you can see, we're going to talk more about this a little bit later, but as you can see, that's making the electrons, behave differently. If we have a weak field ligand, then this electron is able to hop up into this higher energy level. But if we have a strong field ligand, then the splitting, right, it takes a lot more energy from this electron to hang out up here. So sometimes it will instead go down into one of these bottom energy levels. And we're going to talk about how do you know when it does which thing. a little bit later in this lecture. First, though, I want to talk about the colors of transition metals. So I told you earlier that our valence bond theory was not good at predicting the colors of the transition metal complexes. And this is because the color is going to be determined by the crystal field splitting energy. So valence bond theory doesn't take that into account, but crystal field theory does. So it's going to be determined, the color is going to be determined by the crystal field splitting energy of the complex ion. And so we have two different ways that this can show up, right? For a given ligand, so if we have all of the same ligand, then it will depend on the oxidation state of the metal. Again, metals with really high oxidation states, like those 3+, are going to have a larger crystal field splitting energy than some of the smaller, lower charged metal ions. And if we had all of the same metal with all of the same oxidation state, then it would depend on the ligand. Most times in this class, we're going to be looking at the ligand's effect, but we will sometimes look at the metal's oxidation state. So if we look here at this top one, we have vanadium in both of them, okay? And in both, we are having the vanadium bonded to water, okay? So water is the same. We have 6 waters on each, okay? So our ligand is not changing here, so that means the color is based on the oxidation state of the metal ion. So here we have vanadium being a 2+, and we have vanadium being a 3+. Okay, so our color has changed because the oxidation state of the metal is different. Down at the bottom, in both of these, we are going to have chromium 3+, okay, because if you'll recall from before, our ammonias are neutral, so that means this charge here is due strictly to the chromium. Whereas here we have a chloride, so that's balancing out one of the chromium 3+, right, which is why we get this overall 2+. But in both of these here, chromium is a 3+, which means the chromium's not changing. The thing that's changing is the ligand, right? Here we've added a chloride instead of having just ammonia. So the presence of that chloride has changed the color of our complex ion. Okay, so again, the reason that these colors are changing is because they are going to have a different crystal field splitting energy. Okay, so the colors. Let's talk more about those. Each color has what's called a complementary color, and we can see it opposite on this, this color wheel here. So I'm going to refer a lot to the color wheel or the artist's wheel. And the color that the object exhibits depends on the wavelength of light it absorbs. And I actually have a really good picture of this on the next slide. But we're going to look at the color that it absorbs, and then it's typically going to be colored as the complementary colored. For example, if we have something that's going to absorb violet, well, when it absorbs violet, it doesn't look violet. Okay, so when it absorbs violet, it's going to look like the opposite, right? We're going to go across the color wheel, and it'll be yellow or maybe even greenish yellow. Okay, kind of like blue, right? Or, if it's blue, it's going to look more yellow, right? We're going to go across, or you might say orange across, okay? But it's always going to look like the complementary color. If it absorbs blue, that doesn't mean it's blue. It's going to look, usually we're going to look just directly across the color wheel and see what that is. Okay, so here, we have our transition metals that are showing these really intense colors, right? And the way that these colors are being produced, right? If you think back to, Chem 1 or maybe even, Chem 20, if you did the flame test lab, right? These colors are being produced because an electron has jumped up an energy level. If that electron absorbs some energy, it can be promoted to a higher energy state. And we call this an excited state. And so when that electron is promoted to that excited state, it has absorbed some energy. So we're going to look at the amount of energy that that electron can absorb. Okay, and in here, when it's absorbing, it's going from maybe one of those low energies, right? Maybe say our electron was here, and it's going to hop up to one of these higher energy levels. And so the energy that this electron has to absorb to do that is going to be based completely on this crystal field splitting energy. Okay, so when that electron absorbs some energy, it can get promoted up there. But again, the amount of energy that it absorbs is due to that crystal field splitting energy, which is again going to be due to, whatever ligand or the oxidation state of the metal. So here's the picture I was talking about. if we have, an atom or an ion, right, that's going to absorb some energy, and in this case, we have titanium 3+. Okay, so titanium normally has 4 valence electrons. If it has a 3+, that means now we're down to 1. So we're just looking at this 1 valence electron, which is really easy to kind of picture when we're doing this. So we have 1 valence electron, and it's going to absorb some light. Okay, water is a weak field ion, weak field ligand, and so we don't have a ton of splitting here. We have some. It's one of the stronger weak field ligands, so we have a good amount of splitting, but not a ton. And so it's going to absorb a certain amount of energy to take this electron up to here. Okay, and so the amount of energy that it needs to absorb is going to be the colors of yellow and green. So if we look at yellow and green, that's going to go from about 500 nanometers to maybe about 600 nanometers, okay? And so we can see that on this graph, it's going to absorb here, about 500 to 600. You maybe could have said, here too. But it's going to absorb some like yellow-green light, okay? Because of the specific energy. It's going to absorb the energy of light that corresponds to this energy. And that just happens to be yellow and green here. And so when it absorbs those colors, that means it's going to transmit all of the other colors. So it's transmitting, the purple, blue, orange, and red. And if we combine all of those, the purple, blue, orange, and red, you see that it looks like this kind of pinkish fuchsia color, right? Because that's all of those colors together, okay? So again, the color of light that your complex ion is absorbing is not the color that you're going to see. That energy that it absorbs is being used to promote that electron to the higher energy level. All of the energy that's not absorbed, so here, purple, blue, orange, and red, that's going to essentially go through, right? It's going to be transmitted. And that is the color that you will see, not the stuff that's absorbed. So again, those colors that we're seeing are due to the splitting of the sublevels, right? The splitting of those d-orbitals. So again, this is why we don't see, or why our valence bond theory was not able to explain the colors, is because it wasn't taking into account the splitting of the energies that's due to the interaction of the ligands with those d-orbitals. Okay, and we can go through and calculate those wavelengths, right? Because we have energy. We know what this energy is, or, it'll be given to you. But we know what that energy is, so we can use that energy in order to calculate wavelength, because that would be our energy of our photon is going to be equal to our delta here, which is really convenient. And so then we can use this, we can use hc over lambda, or h times frequency, right? And we can calculate the wavelength of light. You have done a lot of these calculations when we looked at chapter 7 in Chem 1, okay, where we said E was equal to hc over lambda, right? We did a lot of those calculations. You can rearrange this. You can get lambda equals hc over E, right? And you can calculate the wavelength of light. Please remember that wavelengths are typically given in nanometers. So nanometers, right, is 1 times 10 to the 9th, 10 to the minus 9th, meters. That would be 1 nanometer. That will be a helpful conversion for you. If you've forgotten, H is Planck's constant. That's 6.626 times 10 to the minus 34th joule seconds. And we have C is, we'll go H. We have C is equal to 3.00 times 10 to the 8th meters per second. And our energy here, this is always going to be in joules. Okay, so that's as much help as I'm going to give you on these. You do have some ALEKS problems that have you do these calculations. However, these calculations have already been covered extensively in Chem 1, so I'm going to say that you know how to do them. If you need a refresher, message me and I'll help you out, but I do think you should know how to do this already. All right. So I was talking to you about the spectrochemical series a bit earlier. The spectrochemical series is just the strong field ligands and the weak field ligands all written in a row. They're written kind of backwards from the way that I like to think of them, but this is our strong field ligand over here, and the weaker field ligands are over here. So remember, a strong field ligand means we're going to get a very large delta value, a very, very large crystal field splitting energy, whereas a weak field ligand does not cause this same, the same gap. When we have a really large energy, that means that it's going to absorb a high energy photon, right? A high energy light, okay? And when we have really, really high energies, that means they are very short wavelengths. Remember that energy and wavelength are inversely proportional, like on this slide, right? Our energy and our wavelength are inversely proportional. So if we have something that's really high energy, that's going to be a really short wavelength. Whereas if it has a really low energy, that's going to be a long wavelength. So if you think about Roy, G, Viv, right, in this order, this is our shortest wavelength, this is our longest wavelength. But again, remember, when it's absorbing energy, that is not the color we are going to see. So if it absorbs, yellow, then you might see blue or, some other color. But you need to look at that color wheel in order to see what color it absorbs. I should tell you, I will give you the color wheel on your exam if I ask a question about colors of light. Okay, let's try a problem. So this says, rank these 3 different complex ions in terms of their delta value and of the energy of visible light absorbed. Okay, I want you to try this out. Go ahead and pause here and see which one is going to split our d-orbitals the most, and then talk about, how that's going to affect the energy of visible light absorbed. So go ahead, pause here, try this out. When you're done, come back and I'll give you the answers. All right, let's go through this. So we have 3 different ligands, right? In all of these, our titanium is always going to be a 3+. So that is not affecting our crystal field splitting energy. That's not affecting the color of light. We're just looking at the change due to the ligand here. So we need to see which one of those is the stronger field splitting ligand. So if we went and we looked at the spectrochemical series, we would see that cyanide is our strongest one here, ammonia falls in the middle, and then water is the weakest. So that means cyanide is going to split it the most, right? We're going to have the largest delta value, and then water is going to have the smallest. Okay, so if cyanide has the largest crystal field splitting energy, that means it is going to absorb the highest energy photon, or the higher energy light. Okay, I didn't ask it, but if I had, that would correspond to absorbing the shortest wavelength of light. Again, remember, energy and wavelength are inversely proportional. Okay, so back to the question though, that means that the cyanide complex will absorb the highest energy of light, and it will have the largest crystal field splitting energy, whereas the opposite is true for the water complex, right? Our hydrated complex, it will have the smallest crystal field splitting energy and absorb the smallest energy of light. Okay, so now we're going to talk about magnetic properties. We've talked about the colors, right? And I told you the 2 things we were going to talk about today were the colors and the magnetic properties. So we've talked about colors, now we're on to magnetic properties, and they are determined by the number of unpaired electrons in the d orbitals of the metal. And you should know this already, right? We've covered diamagnetic and paramagnetic. Again, we covered those in Chem 1 when we looked at electron configurations, right? But now our electron configurations have gotten more exciting because our d orbitals are no longer degenerate, right? Now we have different energies of our d orbitals, and we're going to follow slightly different rules now based on the ligand that's attached to your metal. Okay, so if we think back to Hund's rule states that electrons occupy orbitals of equal energy one at a time. So like if we had our 5 d orbitals of equal energy, then we would go, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? Each orbital would get 1 electron before any get 2. But now we have this splitting, right? We have 3 that are the same energy, and then we have 2 that are a different energy. So we have different rules now. So when all 3 of these are filled, now what, right? So the electron can do one of 2 things, the next electron. It can either jump up here, okay, and it can go into this orbital, or it can go into this orbital, right? And so it's going to depend on whether which case will take more energy. Does it take more energy to pair up with this electron? Because remember, electrons are both negative. Okay, and so they repel. So there's some, we call it pairing energy, this repulsive pairing energy. And so it takes some energy for an electron to add into this orbital because it's being repelled by the electron that's already in there. Well, it's also going to take some energy for the electron to go up into this orbital because it has to go into a higher energy orbital. So we're just going to look at which one takes more energy, okay? And it's going to do the easier one, right? The one that takes less. So we're going to look at, does it take more energy to jump up to the other energy level, or would it take more energy to pair up? Okay, and the relative sizes will determine which one our electron will do. Okay, so again, the electron configuration of that metal will depend on the strength of the crystal field. Okay, so we're going to go ahead and look at those, strong field and weak field ligands again to see how much splitting is happening. If we have, so again, we're looking at our orbitals here. So we had 1, 2, 3, and that fourth electron, right? That fourth electron has to make a choice. Does it go up into the higher energy level, or does it add to the electron that's already in one of them? Okay, if the field is weak, so if we have a weak field ligand, which means that the energy gap is small, this is a tiny, tiny delta, okay, then that next electron will just go ahead and go up here because it's going to take more energy to pair up with this electron than it does to go up here because this energy gap is small. So the these orbitals are not that different in energy from these because we have a really small energy gap. But if we have, say we have the same scenario, but we have a really large energy gap, okay? Well, now instead of, being able to go up to that higher energy level, that energy gap is too large, so the pairing repulsion energy there is going to be smaller than the energy needed to put that electron into a higher energy level. So that would be if we have a strong field ligand. So when we have a weak field ligand, that tends to lead to a lot of unpaired electrons because they're going to, go 1, 2, 3, 4, 5, right? And it can just keep, it can fill in all of those orbitals before any paired up. Well, if we have a strong field ligand, we tend to get more paired electrons because that energy gap is too large, right? This pairing repulsion energy is going to be smaller than the energy it takes to go up into that higher energy level. So we start to seed more paired electrons, and this will lead to a diamagnetic complex. So paramagnetic means unpaired electrons. Diamagnetic means paired. Okay, so let's look at two different examples here. One, we have iron with water, and then the other one we have iron with cyanide. Okay, in both cases we have iron 2+, so we have the same number of valence electrons. So we have 6 valence electrons. Water is a weak field ligand, so that means our crystal field splitting energy is small, whereas cyanide is a strong field ligand, so our crystal field splitting energy is large. So when we go and we put those 6 electrons, right, we're going to go for the one on the left, we go 1, 2, 3, 4, 5, 6, right? Because that pairing energy is larger than, our crystal field splitting energy, that means our electrons will go up here into these higher ones rather than pair up until it has to. On the other example, our crystal field splitting energy is large, especially compared to our pairing energy, so that means our electrons would rather pair up than use the energy to go up to that higher energy level, right? So here we go, 1, 2, 3, 4, 5, 6. So in the case on the left, right, our water compound, this is paramagnetic because it was able to use all of those orbitals before it needed to pair up. Well, the one on the right, our cyanide compound, that's diamagnetic because that splitting energy was so large, right, that it needed to pair up its electrons before it could add any to that higher energy level. So now we have two different terms here. We have a high spin complex and a low spin complex. A high spin complex is exactly what it sounds like. It has lots of spins, lots of unpaired spins. Okay, it has, 4 unpaired electrons here. That's a high spin compound. And this will actually have the same number of unpaired electrons as the free metal atom because they essentially got filled the same way, right? That crystal field splitting energy didn't affect how we paired it because we still put 1 electron in each before any got 2. Well, the other one, our cyanide compound, that's a low spin complex. because we paired up our electrons essentially halfway through, right? We went 1, 2, 3, and then we started pairing 4, 5, 6. So this is a low spin complex because it doesn't have any unpaired electrons. It doesn't mean it has to have none. Low spin complexes mean that it just has fewer unpaired electrons than the free metal atom or free metal ion. But here it has no unpaired electrons because it had 6, so it completely filled up those lower energy levels. I want to point out that only the electron configurations that are d4, d5, d6, or d7 can have a low or high spin. And here, this is d6. Okay, this is telling us how many electrons we have in the d orbitals. Both of these are d6. And so it only matters for d4, d5, d6, d7. The reason for that is if we have d1, 2, or 3, it's not going to be affected by the splitting at all because they have so few electrons. So like if you think about it, right, let's say it had 3. Okay, so we go 1, 2, 3. We never got to that 4th electron, so we didn't have to make a choice of where that electron needed to go. So we don't really classify those as high spin or low spin because our crystal field splitting energy didn't affect our electron configuration. And then D8, 9, and 10 also are not affected by this because those lower level orbitals get completely filled either way. So let's say 8. So we went 1, 2, 3, 4, 5, 6, 7, 8, right? Those low ones got filled that way, or we could have gone 1, 2, 3, 4, 5, 6, 7, 8, right? It ends up looking the same whether or not there was a large crystal field splitting energy or a small one, okay? So only the electrons configurations of D4, D5, D6, D7 we classify as high or low spin because the other ones aren't affected by the strength of the crystal field. All right, so here's what it would look like for D4, D5, D6, D7. So we have our high spin on the left, again, lots of unpaired electrons, and then we have the low spin on the right, which would have fewer unpaired electrons than the normal metal atom would. All right, I want you to try this out. So manganese forms octahedral complex ions in its +2 oxidation state. So for the free Mn2+ ion, okay, so I want you to do this one, and each of the 2 octahedral complex ions. So I also want you to do this one and this one. So you're going to do 3, okay? You're going to draw energy diagram showing the orbital splitting, if there's any, and then predict the number of unpaired electrons, and then identify the ion as low spin or high spin. Okay, so again, you're going to do energy diagrams, predict the number of unpaired electrons, identify it as high spin or low spin. Once you're done, come back, and I will show you the answers. Okay, let's go through this. So for the free manganese ion, right, that Mn2+ ion, we don't have any splitting, right, because there's no ligand on our metal ion, so we don't have any splitting. Remember that the interaction of the ligand with those orbitals is what causes the splitting. If there's no ligand, there's no splitting. So we draw our 5 degenerate orbitals, and then Mn2+, normally manganese has 7 valence electrons, so if it's forming a 2+, that means it has 5. So it puts 1 electron in each one of these, meaning it has 5 unpaired electrons. If we have a weak field ligand like water, that means that the way we fill our electrons is going to be essentially the same as the way we filled it for our free metal ion. So we're going to go 1, 2, 3, 4, 5. And again, that's because the crystal field splitting energy is small enough that the energy to pair them up, right, that repulsive energy is larger than our crystal field splitting energy. So it's easier, right, it's a lower energy cost to put the electrons up a little bit higher than to pair them up. So again, we're still going to get 5 unpaired electrons. So this would be a high spin complex because it has the same number of electrons as the free metal ion. If we have a strong field ligand like cyanide, then we're going to get a very large splitting energy. Okay, and so that affects the way our electrons are filled. So we go 1, 2, 3, 4, 5, because that repulsive energy, that energy of pairing, is smaller than our crystal field splitting energy. So it's going to take more energy to, bump it up to this higher energy level than it does to pair them up. So that means we are going to get a low spin complex because now we have some paired electrons, right? We're going to have fewer unpaired electrons in this complex than we do in the free metal ion. So here we only have one unpaired electron as opposed to the other two have 5. All right, so we've been looking at octahedral complexes so far, but we can also look at tetrahedral complexes and square-planar. Okay, in a tetrahedral complex, the d-orbital splitting pattern is going to be exactly the opposite of the octahedral splitting pattern. So instead of doing, 3 on the bottom and 2 on the top, now we're going to have 2 on the bottom and 3 on the top. So it's exactly the opposite. And the labels on the orbitals, flip as well. So before, the XY, XZ, and YZ were on the bottom, and now they're on the top. Okay, so the ones that were literally the same exact orbitals that were lower in energy last time are now those same orbitals that are higher in energy now. Almost all of our tetrahedral complexes are going to be high spin because of the reduced metal orbital ligand interaction. Okay, that means our delta is going to be small. We have a very small splitting energy. Okay, so they do still split. It's just smaller. And you're going to see that in the picture in the next one. But the reason that it's small is that the d-orbitals in these tetrahedral complexes, these square-planar complexes, are interacting only with 4 ligands, as opposed to the 6 in an octahedral complex. Okay, so we're getting less repulsion, right? So we're going to get a smaller crystal field splitting energy. So here's what it looks like. So if we have the d-orbitals on a free atom, again, are all going to be degenerate. And then when they interact, they're going to split. Again, we're going to have 2 on the bottom now and 3 on the top. And the reason that this happens is, again, because of how the ligand is interacting with the orbitals. All right, now when we talk about square-planar, right, in our square-planar geometry, this has a really weird splitting pattern. Now we have 2, 1, 1, 1, okay? And again, I'm not going to make you know this one, but it is a bit odd, and this is only going to occur for D8 metals, so only metals that have 8 valence electrons when they are an ion. And they are pretty much all going to be low spin complexes because they're usually diamagnetic. So if they have 8 valence electrons, they're going to go 1, 2, 3, 4, 5, 6, 7, 8. So they're pretty much all going to be diamagnetic because all 4 pairs of d electrons are going to fill the lowest 4 orbitals. They're all going to be paired. And so, that's how they're pretty much going to end up. And that's it for chapter 25 in this class. We didn't cover all of chapter 25, as you'll see if you read the book, but we covered the stuff as it relates to what we are doing in this class. So we've talked a lot about complex ions, we've talked a lot about coordination compounds, and we're going to look at their colors and things like that, especially in lab. So it was important to cover these topics in a little more depth. If you're interested, you are more than welcome to read the rest of chapter 25, but these are the topics that we're covering in this class. So today we covered a lot about crystal field theory. We looked at why the orbitals split when they do, right? We looked at, how they might split. We see very large splitting energies associated with strong field ligands and very small splitting energies associated with weak field ligands. We looked at how the splitting energy affects the color of those metal ions. And we also looked at how the splitting energies are affecting the magnetic properties of those metal ions. So lots in this lecture, lots in this chapter in general, especially for only 3 lectures, but I think it's really important to understand more about these complex ions and coordination compounds. Keep working hard. You've got a lot of practice problems in your chapter 25 lecture worksheet, especially with these splitting energies and how they affect the magnetic properties and the colors of your metal ions. So make sure you're practicing those. As always, if you have any questions or you're coming across any problems, please let me know, and I'm more than happy to help you out. Reading the textbook may help you too. I forget to always say that, but that is a great resource if you need it. But of course, I'm always here to help. But keep working hard, and I will talk to you guys next time.